So now let's take a look at the first continuous, random variable, and the corresponding distribution, namely the so-called Gaussian normal distribution. And before we do that, I want to quickly show you two statistical distributions that are likely normally distributed. And one of them is height, which you can see here. So we've divided this here by men and women. The data comes from Wikipedia, which in turn is sourced from a statistical authority. And here you can see in yellow the percentage shares of different groups in terms of height. It's obviously a discrete distribution in this context, but you can probably already imagine what the corresponding continuous distribution might look like. Something like this for the women, and I'll use a different color, something like this for the men. So what we see is that there's kind of that's why it's called that bell curve. So there's a peak, and around the peak it's approximately symmetrical. We see that it's not exactly the case, but it does trend towards being symmetrical, and it flattens out as we move towards the edges. We can't see that very clearly here, but the next value would be close to 0 U-cent. And if we divide it into men and women, then the whole thing is normally distributed. And exactly, we'll also look at why that's relatively plausible in the next video. I brought another statistic with me, namely high school grades in Baden-Württemberg, which look quite similar. So we also have a kind of peak here, and then it goes down like this. All right, we have this peak at 1.0, which is simply due to the fact that there's a cutoff and all the values pile up there. But if there were also 0.9 and so on, then we can already imagine how it would go down like this. And what we've seen in both cases is essentially basic idea of the normal distribution. So the normal distribution is basically a continuous distribution that looks something like this. It has this bell curve, has a peak, and is symmetrical around the whole thing, and it can be narrow or less narrow. And now we need to find a function that describes this. And this is now a bit of a more complicated function, 2001, but don't worry, we'll take a closer look at it. So we call a random variable normal, distributed with the parameters and sigma if it has the following density function. So we want to define the normal distribution, not through the distribution function, but through the density function, which then clearly defines the distribution function. And it looks like this. The most important thing is that we have an exponential function. And then we have minus 1 times x divided by sigma squared. So that's basically our exponential part. And then we have a constant factor in front. That includes sigma, which makes the whole thing even more complicated. Square root of pi. Alright, we don't want to go into too much detail about where it comes from. We mainly want to take a look at what the function looks like. Just to clarify, the parameters and sigma, as you might guess, are the corresponding expected values and the standard deviation of the distribution. We'll also take a look at why that makes sense. We write when the random variable is normally distributed, x tilde n for normal distribution, and then sigma squared. So we specify the variance and the expected value. We call this the normal distribution, or also Gaussian distribution, or Gaussian normal distribution. U-sand and the graph of this density function is often called the Gaussian bell curve because it looks like a bell. Exactly. And sigma corresponds to the expected value and standard deviation. Let's plot the whole thing. First of all, what can be shown is that this function has a maximum at what? Well, at mu. Okay, let's take another look at that. So that means there is a maximum at x equal to, which defines our expected value. And in this case, what we see here is that the expected value is 0. So we have our maximum at the value of 0. And what we also see is that as x approaches infinity and as x approaches negative infinity, these values tend towards 0. And we can think about this for a moment, because when we have e to the power of minus something, and then we have something that, as we approach positive infinity, goes towards positive infinity. So I'll write something like big N here, and that's actually 1 over e to the power of n. And you see, when n becomes particularly large, then it all tends towards 0. And when x approaches negative infinity, well, then x remains positive. So it also tends towards 0 for the same reason. Exactly, you could, for example, differentiate the second function again, and then maybe you can also see why the maximum actually lies there. So first of all, let's look at what happens when we set it to 2. Then it's basically just a shift without any compression or stretching to the right, which means the maximum just shifts. That's one option. And the other option is that, for example, if we choose sigma to be 2, then it becomes wider, but also less tall. Exactly. The reason it's less tall is partly because we have this factor here that pulls everything down, and then we also have sigma, which makes it wider. Exactly. Now we could, yes, and those are the two transformations that we can perform. And now, of course, the natural question we have is whether we can determine the distribution function based on the density function. So, can we determine the area under this density function? Or in other words, can we calculate the integral? So, f would be p of x less than or equal to x. And that would mean we plug in the function and need to integrate. We can pull this factor out of the integral, so we have the integral from negative infinity to x of, well, this function here, which is exactly the function that appears in the density. And we would need to integrate that, which means we would have to find the antiderivative. And the bad news is that it's not analytically solvable, so we can't provide an antiderivative, but that's also good news, because it means you don't have to be able to do it. So you don't have to be able to integrate it, because it simply can't be done analytically. So we can't provide a closed expression for the antiderivative. So that means we need to determine the distribution function numerically. And what does that mean for practice? So we actually need to, when we have a normal distribution, what we do is we convert it into what's called the standard normal distribution. So the standard normal distribution means that the mean is 0 and sigma is 1. And then we can look up the results in the tables in such a reference book. Maybe you remember that from school, or you can find the corresponding entry on Wikipedia. But that means this is the way to calculate the probabilities in the normal distribution. Let's take another look at it graphically. So if you want the distribution function at the point x equals 1, then, as you already know, it's the area up to that point, which is 1. Even though we can't calculate it, there is still, as I said, this trick that allows us to convert it into the standard normal distribution. So let's define this briefly. It gets a special name, the standard normal distribution. So a random variable z, we often write z for the standard normal distribution, is said to be standard normally distributed if the mean is 0 and sigma, or equivalently sigma squared, is 1. And then the density function can be written a bit more simply as 1 over the square root of 2 pi times e to the power of minus z squared, and we call that little phi, and we denote the distribution function with big phi. Exactly. And that's exactly as I said, this integral, and we can't calculate that either. It's not that we can calculate it all at once, but we can calculate it numerically. So not analytically, but we can calculate it numerically, and you can look that up in reference books. Okay, the question is twofold. What can we do now? Can we use any more formulas? We're going to do that now, but how can we translate a normal distribution into a standard normal distribution? Exactly, so we can't calculate big phi, but we can, based on the symmetry properties, for example. Prove the following. Formula here, phi of minus z is equal to 1 minus phi of z. And let's think about that for a moment. Why is that the case? So imagine phi of z. Let's take an example. Z is equal to 1. Then phi of minus z would be this thing here. And what we see is that this is phi of. So this area here is phi of z. And now we can take a look at what phi of z is. Let's maybe do that with a blue one. So phi of z would be essentially this whole area up to here. And what we see is that phi of z plus phi of minus z, y is equal to 1. Because this red area here, we can see that again due to the symmetry. And that means that the red area plus the blue area is the total area, and the total area is equal to 1 because it's a probability density. And then they have exactly the property they want, that phi of minus z equals 1 minus phi of z. So you see, we can't calculate it, but you can still prove certain identities by using the fact that it's symmetric, meaning it's symmetric around the mean. So now the last sentence for today, and then we're done. So if x is normally distributed with the parameters mu and sigma, we can get a standard normal distribution just by taking x, subtracting mu, and dividing by sigma. And then we get a new distribution, which is standard normally distributed. This means that if we want to calculate the distribution function of x, and we know the distribution function of z, we can calculate the distribution function f by plugging in pi, but instead of x, we use x minus a mu divided by sigma. And then we get a new distribution. And that one is standard normally distributed. So that means if we want to calculate the distribution function of x and we know the distribution function of z, we can calculate the distribution function f by plugging into phi, but not using x, rather x minus mu divided by sigma. And almost the same goes for the density function, except you need to add a 1 over sigma there. This means that if you know big phi and little phi, then you can calculate the values for the distribution function and the density function for any normal distribution. And almost the same goes for the density function, except you need to add a 1 over sigma there. This means that if you know big phi and little phi, you can calculate the values for the distribution function and the density function at any point for any normal distribution. And that's exactly your task for the exercise sheet. So that's exactly what they should do. And as I said, for that you need the reference table. So you need to know the values of big phi and little phi. So that was the brief excursion into the normal distribution. So this week we have, as I said, now learned about the most important distributions. Hypergeometric distribution, binomial distribution as two very important discrete distributions, and now the most important continuous distribution, namely the normal distribution, where you can see that the whole thing is relatively complicated. You can't even specify exactly what the distribution function is. You can only specify the density function. And yet, and we will see this next week, the normal distribution is one that occurs everywhere in nature, and that plays a very, very important role. What exactly that means and what it looks like is something we will look at next week. Until then, take care.